Hello everyone, I am Kirti Amolik from Assistant Professor in Chemistry Department of RBNB College. So in the previous lecture, we have started the first order reaction, characteristics of the first order reaction and the problems based on the first order reaction. Now next point, it is the second order reaction. Now second order reaction, the rate equation, it shows the exponent of it is of value 2. So when the exponent of the concentration term it is 2, when one reactant is involved in the reaction, it is called as the second order reaction. When two reactants are involved in the rate equation, then these two reactants having the one exponent in the concentration term, then 1 plus 1 it becomes 2, so it will be second order reaction. So in the second order reaction, when one reactant is involved, an exponent of the concentration term is 2, and if two reactants are involved in the second order reaction, then it is exponent it is 1. So exponent 1 is given for each reactant, two reactants. So 1 plus 1 becomes 2. So it will be second order reaction. Now we are going to study the mathematical expression for the second order reaction, as earlier we have seen in the first order reaction and zero order reaction. So we are considering first the general reaction. So let us consider the general reaction. A gives the product. A gives the product. This is general reaction in which the reactant is 1. So if we consider the examples of the second order reaction, so basically three examples are given. In these three examples, first is the it is the thermal decomposition of the ethylene or hydrogenation of the ethylene molecule to corresponding ethane molecule. It is corresponding ethane molecule. Second example is alkali hydrolysis of the ethyl acetate, alkali or the basic hydrolysis, that will give the hydrolyzed product, that is methyl acetate is formed and ethanol is formed. Third example is the thermal dissociation of the hydrogen iodide to give the hydrogen and iodine. So these three are the examples of the second order reaction. As we can see here, two exponent of the reactant. So exponent of the rate equation it is 2, because coefficient, stoichiometric coefficient it is 2. So this experimentally determined second order reaction. Now let us consider the mathematical expression. For this we have to consider the general reaction. A gives the product. Now in the second order reaction, as the exponent is 2, so either one reactant may be involved that having 2 coefficient, or two reactants may be involved that having the 1 each coefficient. So after one addition of 1 and 1, it will give the 2, so it becomes second order reaction. So in this case we have to consider the two cases. The first case in which only one type of the reactant is involved, so its exponent of the concentration term in the rate equation it is 2. If two reactants are involved, the exponent of the concentration term of these two reactants it is 1. So 1 plus 1 it equals to 2. So it is second order reaction. So at first we are going to consider the first case in which only one type of the reactant is involved. So according to law of mass action, rate of the reaction we can write, if the concentration of this reactant A is Ca, concentration of the reactant is Ca at time t, then we can write rate equals to minus dCA upon dt. So in each expression we have written this type of rate equation, minus dCA upon dt equals to K2, or it is proportional to concentration. So proportionality constant is 2, K2. So it is the second order rate constant into Ca raised to 2. Now Ca is the concentration of the reactant A and exponent is 2 because coefficient is 2 here. So as the exponent is 2, it is the second order reaction. So this is the basic rate equation. Now further we can take the derivative and further integration for this equation. So we can write further the value of the Ca. So if we assume, let the A mole is the initial concentration of the reactant, small a is the initial concentration of the reactant, and small x mole is the concentration of the reactant that is going to react in time t. Then the unreacted concentration of the reactant, or it is known as A minus X. It gives the unreacted concentration or the final concentration of the reactant. So A minus initial minus reacted, it will give the unreacted concentration or final concentration of the reactant. So we can put this value into the equation. So Ca becomes A minus X, that is the final concentration of the reactant. So rate equals to minus d A minus X dt. So it is equal to dx upon dt, that is the concentration of the reactant which is reacted, equals to K2 into A minus X, which is nearly equal to Ca. So Ca is equals to now A minus X, the final concentration of the reactant raised to 2. This is equation number first. Now if we rearrange this equation now, in order to take the integration, x terms are considered are taken on the left side and the t term it is taken on the right side, and further constant K2 is also present taken on the right side. So if we rearrange this x term, if we A minus X raised to 2, it comes on the downward side denominator when it is shifted to the left hand side. So we are getting dx upon, and this dx upon A minus X raised to 2 equals to K2, and this dt which is present on the left hand side, it is goes to the right side. So from denominator it goes to numerator. So it becomes K2 into dt. Now next, further this integration can be taken for this equation. The integration can be taken from the limits x equals to 0 to x equals to x, and for the t it is t equals to 0 to t equals to t. So we integrate this equation within these limits, then we are getting integration of dx upon A minus X raised to 2 equals to K2 into dt. Now this K2 term, it is the constant, second order rate constant. So it is taken out of the integration. So we are getting this. Now by applying the limits here, we can write into square bracket 1 upon A minus X within the limits equals to K2 into t within the limits t0 to t. So by solving this equation, A minus X, we are getting 1 upon A minus X into 1 upon A equals to K2 into t. So t initial final concentration minus initial, we are getting the t. So further now this equation we can write it as x upon A into A minus X, this quantity equals to K2 t. So we are going to determine the value of the K2. So we can write this K2 t. So it is shifted on the left hand side. So it comes on the denominator. So therefore it becomes K2 equals to 1 upon AT into X upon A minus X. So it is equation second. So this equation second, now it gives the K2, that is the rate constant for the second order reaction when one type of the reactant is used or single reactant is used, in which the coefficient, stoichiometric coefficient is 2, or it may not be 2, but the exponent term should be the 2 in the concentration. So this is the case first, and we have derived the equation. Now let us consider the case second. So we can take this equation. In the case second, the two reactants are involved. If these two reactants, we can write the reaction. A plus B gives the product. And for this, if we consider the two reactants, these having similar initial concentration. In that case, in the case second, if we consider these two reactant, again further two cases can be considered for this two reactant reaction. Case first, when the two reactants having the similar initial concentration, and in case second, they having the different initial concentration. So further these two cases may be considered. So let us consider the first case, in which these two reactant having the similar initial concentration. So let A mole will be the initial concentration of the reactant A and B, and X mole will be the concentration of A and B that reacts in the time T, and A minus X, it is the final concentration of the final concentration of the reactant A and B, or it is nearly equal to the final concentration or nearly equal to the Ca, or we can assume as the final concentration for A and B also. So from the law of mass action or rate equation, we can put this value. So it becomes minus dA minus x upon dt equals to dx upon dt equals to, it is proportional to A minus x raised to 2. So proportionality constant is given, K2 into A minus x raised to 2. So this is equation third. Now this equation further it can be calculated just similar we have seen in the case first, and we are further getting the same equation, that is after taking the integration for the first. So it is similar to case first. So we are getting the equation, final equation again, K2 equals to 1 upon AT into log of x upon A minus. So similar equation we are getting if we solve this equation similar to case first by taking the integration within the limits for x and t. So it is not necessary to write it again. Now we consider the second case in which A and B, this A and B having now the different initial concentration. So in that case we can put let A mole be the initial concentration of the reactant A and small b mole be the initial concentration of the reactant B. Now we can say that the x mole of the reactant is react in a time t. So unreacted for the A is different and the unreacted for the B is different, that is final concentration of the reactant is different. So final concentration of the A becomes initial minus reacted A minus x, and final concentration for the B becomes B minus x. So we are getting the different values here, A minus x and B minus x of the concentration term. So let us put this value. So we can write in the rate equation minus d of A minus x divided by dt equals to, it is equals to, for the another reactant we can write minus d of B minus x divided by dt. Further dx upon dt we can write reacted concentration proportional to, therefore constant K2 into A minus x into B minus x. So in this equation we have to consider the both cases, that is both final concentration for the both reactant which is different A minus x. In the first case only we have taken the a minus x raised to 2. So here the exponent is 1 and here exponent is 1. So 1 plus 1, it becomes second order. Now we can write this equation for the, we can take the integration for this equation dx upon. So we can, these terms of x can be shifted on the left side and dt, t term should be on the right side. So dx upon a minus x into b minus x equals to k2 dt. So further we can solve this equation by taking the integration and log. We have not shown here because it is much more complicated. It is not necessary to write directly. We can put the values here. K2 equals to 1 upon a minus b into t log of b into a minus x divided by a into b minus x. So by making the log to the base 10, we will get K2 equals to 2.303 divided by a minus b into t into log of b into a minus x divided by a into b minus x. So this K2 is the second order rate constant when the initial concentration of the two reactants are different. So we are getting the two equations here. First equation, this is first equation for the one reactant is involved and here two reactant that having the different concentration. So these two equations are said to be the, we can determine the rate constant, second order rate constant for the reaction. So this is the mathematical expression. Now next is the characteristics of the second order reaction. So always we are studying the characteristic. There are 3 points are given. That is, first is the by graph or the nature of the graph. Second is the half-life period and third is the units of the rate constant. Now let us see the graphical method for the second order rate constant. Now, so we have to consider both equation. Now we are getting here two equations. So we have to consider both equation for the plotting the graph for the second order reaction. So let us consider the first equation now. This first equation, it can be given here K2 equals to 1 upon 80 into log of x upon a minus x. So if we plot the graph of x upon a minus x versus time, that is t, or also we can plot the another graph if we rearrange the equation, but we are going to consider this x upon a minus x equals to, if we rearrange this equation, we are getting x upon a minus x. So this log and 80 will goes on this side, so it becomes multiplied to K2 and this becomes this log. If we change the log of the equation, then x minus x upon a minus x is obtained. If we remove the log, we are getting the x upon a minus x. So if this term x upon a minus x, it is plotted against the time, we are getting the equation which is the straight line equation. It is here straight line equation. So straight line equation is obtained. Straight line equation, it is similar to y plus mx plus c. Y is equals to mx plus c. So straight line which passes from the origin we are getting. If we take the slope on any point of this line, the slope equals to the AK2. AK2 is becomes the slope. And from this value we can calculate K2 equals to slope divided by A. So we can calculate the second order rate constant by graphical method. So this is the first graph given for the first equation. This for first equation. Now let us consider the second equation. For the second equation, that is this equation, we can solve this equation and it can be shown here. The graph is given. Now let us see this graph. So this equation, the second equation, it is rearranged to get this log of a minus x upon b minus x equals to k2 into a minus b divided by 2.303t minus log of b upon a. So it is similar to the equation y equals to mx plus c. So from this is the equation for this straight line. So y is equals to this a minus x divided by b minus x log of, and m equals to k2 into a minus b 2.303, this is value of the m, and the c equals to minus log of b upon a. So if we plot the log of a minus x upon b minus x, this value versus time, we will get this straight line graph, but it is present at this point and we are getting the intercept, and this is intercept is equals to b upon a minus b upon a. So this is the value of c is intercept, so it will be minus log of b upon a. And if we take the slope is m, so m, and x is the t. So this value, it is of m, it is the slope. So slope equals to k2 into a minus b divided by 2.3. So this, from this value we can calculate the rate constant as, we can write k2 equals to slope into 2.303 divided by a minus b. So from this graphical method, second graph is plotted, and from the slope we will get the value of the k2. We can calculate the value of k2, we can put this value and we will get the second order rate constant. So in the mathematical equation, by solving the mathematical expression, we will get the two equations here, and from these two equations we can calculate the value of second order rate constant. And by another method, it is differential method, by taking derivative we will calculate, we have derived the second order rate constant equation. So it is differential method, and another method is the graphical method. So in the graph we have rearranged this equation into straight line equation similar to straight line, and we have plotted the graph, and after plotting this graph, so from this graph we can determine the value of k2, that is second order rate constant. So this is all about the order of the reactions. So this topic is completed here. In the next lecture we will study the Arrhenius equation, transition state theory and the collision theory. Thank you.